All right. So we are finally going to go back to the Smalltalk and Fortran examples we covered a couple of lectures ago. But before that, a couple of things we want to say about what we talked about interfaces in the last class, right? If you recall, we looked at a bunch of interfaces and sort of described how there are ways to systematically think about what is a good interface, what is a bad interface, and the fact that this is very important, right? So just two comments about that which I think are important. One is you may think, oh, this is just really hard. I mean, it took Alex 20 years to come up with the perfect interface for rotate. To what hope do I have, right? Or even the C++ standard committee didn't notice the copy n issue. I might as well just give up, right? That is not the case, right? Our task when we are doing our day-to-day programming is not to come up with a new algorithm or a new way, a new abstraction, a new something, right? For the most part, what we are doing is implementing well-known concepts in some sense, right? Our real task is to figure out, to recognize things that have already been described, things that we already know the right interfaces to, and to write them. So really, it's it doesn't mean that you shouldn't try to do this, because really our task for most of our real jobs is to recognize what has been done. I mean, like as Isaac Newton said, the reason I have seen further is because I stood on the shoulders of giants, right? So people like Hoare and Dijkstra and Knuth have done this work for us. They have told us, here are the basic blocks. This is what you need to put together, and we need to be able to recognize those things and put them together well. Right? So that's one thing. The other thing that I think is important to mention is we talked about rewriting and how important that is. And some of you, when you hear the word rewriting, might be thinking, oh, rewriting is, I mean, you take some application, let's throw it away and rewrite it from scratch, right? That, of course, is a very expensive thing to do and hard and all that, right? And I don't have the time to do that. But that is not what we are talking about. What we are talking about is, hey, I wrote some code, and I realize now that it's not quite organized the right way. It's maybe if I put some functionality into this function rather than there, it would be easier to do, right? So we are rearranging what you've already written, and that is actually very easy, right? You have just written it, you know what it is doing. If you rewrite it at that point, it will be probably more correct, certainly easier to work with, and it might actually save you time. Certainly in the long run, but maybe even in the short run, right? Because it will be better organized, better to test, fewer chance of bugs, etc. And in any case, how much time do you spend actually writing code, if you think about it, right? In terms of your, maybe like Nick, you probably spend 10% of your time writing code.
So I think that's kind of, I kind of think of it as code tidying, and you want to, when the code is in your head, like you're never going to go and just say, I'm going to go cold and clean up my code base. But when you're making a change that uses a library function, for example, and you realize, oh, this function could be generalized, then it's in your head. You're already making this change, you're already working, and it's a good time to fix the library function. And maybe you have to go find some other call points and fix them too. But if you don't do it then, when it's in your head, you're going to pay the cost of getting that library function into your head already.
Yep, that's a very good point. So it's if you've just rewritten it, or if you're making a modification to something that already exists, and you realize, okay, with this modification, the way it was laid out doesn't make sense anymore. Go and fix it. Because at that point, fixing it is only a matter of rearranging code that already exists. It is not an expensive thing. It's very easy to do. Right? It's like if you're writing a paragraph in an email, you write your first draft, it sucks, you rearrange it. You do it all the time. This is something we need to do, and it's very important. Right? Okay, so with that, let's move on to what we did with the, if you remember, we were counting bigrams. So the task was we had a file. A bigram is a sequence of contiguous, a pair of contiguous words in the text. We were counting bigrams in some text, right? So how often does the bigram, thou shall appear in Shakespeare, right? That's what we were doing. And we had two algorithms. We had what we described as the Smalltalk style, which was we parse in the file, and for every bigram we keep a associative structure. We were using a map, which is a red-black tree, to keep a count of how frequently we have seen that bigram. And at the end of the process, we sorted them by inserting them into a set, and then traversing the set from, I think, the end to the beginning or something. And then we had an alternative implementation which we described as the Fortran style, which used only arrays. Right? So we read in all of the bigrams, put them in a big array, we sorted all of them so that multiple instances of the same bigram were together, we counted them, copied the whole thing into another array, sorted the final array, we had our counts, right? Sorted by count. So, and we observed that our Smalltalk implementation, just to remind you, was about 10 to 15 times slower than our Fortran implementation. Right? This takes about 2 seconds, 1 second, something like that. Sometimes it's 1.9 something, so 2 is close enough. Fortran 3, this takes 0.15 seconds, so very fast. Right? Okay, so we want to look at why that is the case, right? And a lot of you tried different variations of this, and we will look at those variations as well and see what worked and what didn't work, etc. But first, let's start with just these two and see what's going on here, right? So let me draw what we were doing in the actual data structures we were using in the Smalltalk example, right? We had, we read in a string. We didn't want to keep multiple copies of the string around, right? So the first thing we did was we put the string into a map, right? So that we can refer to that without making copies of it. So the map is a red-black tree, as I said. So what is a red-black tree? It basically consists of a node that contains a left pointer, a right pointer, the object itself, and probably some other metadata relating to how to keep it balanced, etc. Which I'm sure Alex can tell us about it. Color. Is it red or black? Yes. And in our case, the object is a string, which I believe, at least in the standard library, does not use what's called the small string optimization. So really, this is going to contain a pointer to an extent that contains the actual memory, right? And it'll probably have, again, there are two implementations. You could keep a size here in the object, or you could keep a size here. But again, let's not get into that right now. Okay, so we put our word into this map.
Both the node and the string reside on the heap. And most likely spread throughout memory, because you get first string, then the node, then another string, so they're intermixed.
Okay, so this is our this is what we called, I think, lexicon or words or something, right? So these are our words. Then we had another tree that contained bigrams, right? What was in that tree? That was another red-black tree. So each node is a left and a right, some metadata, and the object was a pair, because a bigram is 2 words, and this was 2 pointers into our words dictionary, basically, right? We had iterators to a tree, which an iterator to a tree is just a pointer to that node, so it's 2 pointers. Right? So we had this data structure. And then finally, to actually sort all the bigrams at the end, we had a count as well, right? So there's probably a third thing. No, we don't have, yeah, we have a count. So this would be count and the right pointer. And finally, we had one more tree, which was called count bigrams or sort bigrams or something, right? Which was, again, left, right, and then just a pointer to this node, because if you want to compare, we can just go to this node and look up the count here, right? So let's walk through the algorithm to see what it did. Right? We got a new word. We call malloc, get this whole string things, this thing set up. We insert it into this node, this tree. So to insert it into this tree, what do we need to do? We go to the root and see, okay, left or right. To decide that, we need to do a string comparison. What does that mean? That means we follow the pointer in the root node to the string, do the two comparisons, and again at every node we need to follow our pointer to the string to do our comparison, right? Okay, so we find out whether it's there or not there. If it's there, we know where it is. If it's not, we add it. We are done. Fine. So we have our word. Next, we construct this bigram, and we are trying to insert or update the bigram index, right? So the same thing. We go in here. At every node in the tree, we have a pair of words that we need to compare. So at every node, we say, okay, first let me compare the left word. How do I do that? Let me follow this pointer to this, and then let me follow this pointer to this, and now I know whether the first word is less or greater, and then sometimes I might want to compare the second word, in which case now I follow this pointer, and so on, right? So you have at least, for every node, you have at least 2 dereferences, right? And this, of course, is logarithmic, so at the lower levels, you're going to go through at least, I'd say, a dozen or so, depending on what the sizes are. And as Alex mentioned, all of this is on the heap. So it's very likely that if it doesn't fit in your cache, every time you follow a pointer, you are missing.
Both the node and the string reside on the heap. Mm-hmm. And most likely spread throughout memory, because you get first string, then the node, then another string, so they intermix.
Actually, looking at the code is a good thing to do here, because it shows us how simple this stuff is to write. Right? Here's our access into the first B tree. Here's our second one. And again, each of these is you're walking the tree to get to it and doing all the comparisons we talked about.
Well, the remarkable thing is that you do not see anything which Param just explained to you.
All you see is a plus plus.
Appears on the code. It's very nicely hidden someplace. Therefore, you just write it, sorted bigrams, insert, and it happens. Something. You don't really know what.
And then finally, we do this. Here, of course, every time we compare, we have one additional dereference. You go from here to here. Okay, so this is why this code is expensive. It's for every basic operation, we are doing like 5 dereferences. Well, actually, for every individual node, we are doing a whole bunch of dereferences. And then to do any tree operation, we are going to walk through the tree. So we're going to touch who knows how many nodes. So if you add up the number of cache misses here, I mean, it's truly mind-boggling, right? What we're actually doing here. And many mallocs as well, yes. Since the number of unique bigrams is probably, well, yeah, we probably do a 1 malloc in any case. We probably do a bunch of mallocs every iteration. You're right. Yes. Because I suspect when we do this, we might actually, well, I think the string will, if the string is already big enough, it may not do a malloc. It depends on the string implementation. Yeah. So anyway.
The number of mallocs is linear. Not
yes.
n log n.
Yes.
That's the important thing. The number of comparisons is n log n.
But in any case, let's say the total number of words, the total number of individual bigrams is n, and the number of unique bigrams is k, right? It's still, on the whole, this is a n log k operation. But the constant may be big, but it's n log k, right? Now let's look at the other one. I don't know if I want to show the, well, maybe I should show the code for that, but. Okay. Right. So here we create one array that contains word 1, word 2. That's it. That's our first array. It's a big array, but we only write into it sequentially. And we don't, well, it's a vector, so we malloc every time you need to double, but that's logarithmic?
Well, actually, for data, we don't have a vector.
We do have a vector over here, I believe, this thing. The data itself is a map.
Data itself
Yes.
is M-mapped. There's just an
Yeah, but this thing is a vector that we insert into. Then we sort this, and we create another vector that contains W1, W2, and count. Right? And we sort this, and we have our sorted list of bigrams. So even just purely in terms of total amount of memory used, these are actually probably fairly, I mean, I think the Fortran solution is probably going to use less memory, because if you look at the amount of overhead here, a pointer on a 64-bit machine is, what, 8 bytes, right? So you have 8 bytes here, and 8 bytes here, and at least probably 16 by either 8 bytes here and the length here, or in many cases, if the length is stored in the object, it's even worse. You have a length as well. And again, you have these 8 bytes. I mean, count the number of pointers here. It's horrendous, right? So this is wasting a huge amount of space. It is doing so basically non-local reference. Dereferencing is expensive anyway, because even if this stuff was in your cache, right, the number of loads you have to do to do each comparison, you need to do 3 dereferences. That's going to cost you. I mean, yes, it's going to cost you less if it's in your cache, but it's still going to cost you. And if it's not in your cache, then each cache miss is going to cost you 100 to 200 cycles. Right? Your process is going to be sitting there waiting, like, okay, when is my next thing going to come back? And as soon as it comes back, you do another memory reference, which again misses in your cache, and again you sit there, okay, whereas what do you do here? When we are reading data, we append in order. And again, in order appending is really good because all caches will do prefetching. So in order reading or appending, it's all very good, right? And then we do quicksort. And quicksort is actually, I mean, it has a lot of wonderful properties, but one other wonderful property it has, it is amazingly good for caches, because think about what it does. We partition the array first, right? And then we need to, we pivot, we find a pivot and we partition. How do we partition? We walk from both directions sequentially. So even though the array is very big, it may not fit, but we are still accessing it in order. So it's, the prefetcher is going to give you a lot of benefit here. And then even better, once you get to smaller sizes, your array fits into your cache. And then at the lower layers of the algorithm where most of the work happens, you are in cache, right? And you sort all of this before you sort all of this. And so this is actually really good, even if the data set you have is very large. So I mean, if you remember, okay, we'll go to it later. If you remember the sort benchmark that we looked at, where we did quick sort for a large number of sizes, the multiplier stayed the same all the way from 8 entries to 1 million entries, which is pretty remarkable. That means, I mean, we know that we have this, memory is not a random access, but for some reason the multiplier stayed the same. I thought that's very. We'll come back to that point. But basically, that is why this code is over 10 times faster than this code. That's what's going on here. And okay, so let's discuss the various things people tried, and I think there are many. Yes.
This the array-based solution doesn't have all the complete words. It only has parts of the words. So there's a correctness issue.
Yes, and there are so one thing you can do is
encourage English speakers to not use words longer than 8 characters long. I think that would solve.
You can make the words longer. You can make the words longer. So if you say, okay, 8's not enough, make it 12.
By the way, just show the data. We have multiple Fortran solutions.
Yes, we also had a solution where what we did was the data.
Show the data. The easiest thing is to go to my mail and
Exchange.
For example.
Do we have network?
Go to Google, Gmail. Go to Gmail.
All right, so Chetan did this wonderful thing where he gave us all the timing. So the fastest one, Fortran 3.cpp, was 0.26 seconds. We had another version called Fortran 2.cpp, which is 0.4 seconds, slower but still pretty fast. What that was doing was, for each word, we had a prefix which was 8 bytes, and a pointer, so basically another 8 bytes, to the remainder of the word. Right? So we doubled the size of this array basically. And so if the word fits, we put it in there, otherwise we have a pointer, and we only need to follow the pointer if the word doesn't fit. And there are very few words in English that don't fit.
But so Fortran 2 then is the reasonable version to use in comparisons, because Fortran 3 is just not correct.
Absolutely not true.
I would argue.
Absolutely not true. Think about what really goes on. You are saying that here we're losing precision, and we do. But what will happen in your wonderful search engine if you do that? Yes, you would lose precision, and the match set will increase. So you will get hits which you shouldn't. That's not a problem, as long as you're not losing things, right? Yes, you occasionally, if there is a word Harry Potterism, it will be exactly matched with the word Harry Potterismus. This is Latin version. I don't think the people who search for one and get the other one will be terribly upset, right? So what we're trying to establish, this is why this number is very important, because it gives you a lower bound. You know what you could strive toward, right? Yes, you need to understand the ramification, but you also need to understand 27 versus 1.8.
I mean, you're right, it depends on the application, but you need to be aware that in many cases you don't really need to be perfect, and moreover, in English, really the first 10 letters match. How many words are there where the rest of the word is not going to match?
So if we're talking English language and search engine, maybe, but if we're talking bigrams in DNA, for instance, maybe not so much.
Maybe not so, but then you would increase the size. Again, we're not telling you that these are ideal programs, neither this, nor this, nor this, or any of them. These are toy programs. But you're trying to get a sense, as we hope you do, of what is the difference between this and this, okay? And since we see in our search engine, and in lots of other pieces of code, in all over the world, in Google, in Adobe, whatever, we see this style, and we see this kind of numbers. People freely use maps, yes?
Including in the search engine.
It's not that I'm sort of artificially using maps. You know, I have been shocked. I remember when I joined Adobe in, when did I join Adobe? 2001? 2002. I started looking in the code. And what do I see? I see maps of maps throughout, everywhere. Because people not just discovered them themselves, but they were taught. They hired some professor from San Jose State who taught them STL. And he explained to them that you could do these wonderful things. You could have maps of sets of vectors, or vectors of maps of sets. By the way, it all works. It's my fault, but I made it so that it works. But it doesn't mean you should ever do it. Yes? And you say, well, we don't do it. Yes, you guys do it.
We particularly went through the code looking for like maps of maps. We stopped after, I don't know, half dozen or so. And if you just look for maps, there are so many maps in our search engine.
Some of you might remember the work remember Ryan Ernst, who is right now traveling on business. So Ryan and I did this work for finding performance bottlenecks in the search engine. What basically we looked at places where there were lots of maps. And you say, oh, only stupid programmers. No. What we discovered, there was a direct correlation between how great the programmer is and how complicated stuff he uses, like maps of maps. I don't want to name names, but these were not low performance, right? And people used that. So it does happen. So what we are trying to say is, yes, occasionally you could use a map. Occasionally you could even use map of map. This is not the point of the course. Never use maps. But you have to be aware there are consequences. These are complicated data structures. Right? Complicated data structures are expensive. Here, I'm going to for a diatribe now. Sort of what is the point of the course? The point of the course is that Fortran was a great language. Did it have maps? Anybody know? No, it had no maps. Did it have lists? No. What data structures did it have? Arrays. Okay, and people were able to do wonderful, wonderful things. Right? And the code was fast. So, since one of the potential subtitles for our course is Back to Fortran, what we are trying to convince you guys is that the arrays are good. It's a very hard argument because you have been brainwashed for decades by very clever people that you should not use arrays, that something is wrong with arrays. Because even as far back as the 50s, clever people realized that arrays are bad and everything could be made out of pairs, which they called conses. Right? And they created truly the universe where you were supposed to create everything out of little nodes. I'm not making it up. You know, they were teaching young children that you're supposed to use lists everywhere. That cons was the sort of quark of the programming universe. Yes? They were publishing books which were saying you have to have cons, lambda, indefinite extent, and proper tail recursion, and you're done. And people, not just at MIT, but even at sort of inferior schools such as Berkeley, were taught, Berkeley is a great school, it's a joke, were taught that as their first programming thing, that cons is the basic thing, that you should view the world as a collection of pairs. And arrays were just for them physicists. Computer scientists are not supposed to think in terms of arrays. So what we are trying to do is to bring back the sense that arrays are good, that algorithms on arrays are more important than advanced data structures. People come to me and say, but wouldn't it be wonderful if, you know, we had leftist trees on top of red-black trees? I don't know. I don't think so. You know, I don't think that by bringing more advanced data structures will make the world better. I think that building more array-based things will make the world faster. Moreover, I actually think that thinking in terms of array with indices is a better way of thinking. This is obviously, you know, whatever little credibility I still left with the brainy bunch, I'm going to be sort of losing right now. But I actually claim that thinking in terms of array indices is oh so much easier than thinking in terms of recursively based data structures, right? So, and that's what we're trying to just say, look, you could write code like that, it will take so much time, or you could write code like that. Maybe you will get, by the way, you could get precise answer and still win by about a factor of 10. But if you move all the way, and the beauty of that, there are actually no pointers anymore. We put everything in there. Yes, you lose some precision. Some bigrams are going to get sort of wrong counts. Not by much, by the way. This is not, when we say wrong answers, well, they're almost right answers.
Yeah, I mean, you have to be, you shouldn't slavishly say, no, we must get the exact. You should know what your application is. in some cases you can tolerate a few counts here and there. Do it. Why not? You know, it's yeah.
Yes.
You need to make those trade-offs exactly.
But again, sort of this entire thing is beware of advanced data structures. By the way, again, you know, I'm making the case stronger than it should be. Yes, sometimes it's good to use advanced data structures. After all, you know, I gave you this advanced data structure which you are abusing. So obviously, I'm not the enemy. But on the other hand, you should beware of the costs. You should understand that it's expensive. And it's not expensive in C++. It's expensive in Java. It's expensive in Python. Everything is expensive in Python. But
no, well, it's interesting that Nick's
well,
first Python
we will
implementation.
get there.
Yes.
We'll get there. They have to learn not to take me seriously.
Yes.
So should you.
Yeah. No,
So
I'm well aware. Yes. So actually, the other subtitle for our course that we thought of was node-based data structures considered harmful, because really that does, in a nutshell, cover all of these issues. Because what is wrong with this data structure? The problem is it is node-based. It is on the heap. It is not contiguous. It has pointers all over the place. That is what's wrong with it. That is what is leading to all of these problems. Right? Node-based data structures considered harmful.
But
So-
as any considered harmful, it needs to be taken with a grain of salt. Again, yes, one should not use Go too frivolously. But if you really want to go someplace, Go to is the easiest way of getting there. This is not mine. This is actually Ken Thompson. Right? The fastest way of going from one place in the code to another is by using Go to. You know, people come up and say, no, I shouldn't use Go to. I should put a gigantical if. And just, no. If you want to get someplace, go there. This is, you know, and there are a few cases, like Paul and I found, like, I think 2 cases in the entire programming universe where go-tos are needed. So it's not much. Usually you could get by with while, and if. But if you need it, you need it. The same thing, you need advanced data structures, use them. But first think.
And you have to be careful here, because remember, when we first looked at this problem, right, it's very easy to convince yourself that we are counting bigrams, we need to keep a count. I mean, obviously we need an associative data structure. How else would we do it? Right? It's very easy to, since we are just used to thinking like that, it's very easy to get into that mode and think, oh, here we need an associative data structure. But really, there are very few cases where you really need, I mean, okay, if you have a B-tree index on disk, and you need to be able to query it at the same time as you're updating it, it's probably a good idea. But, you know, in many cases, if you need the counts only at the end, like in this case, or if you're doing all your updates once and all your lookups later, often you don't need really a recursive data structure.
Sorry.
Okay, so before we have lunch, I want to talk about the various things people tried, because I think those were very instructive. So first, let's talk about yes. Oh yes, so this thing that Chetan did with all of the timing all of them on one machine, that was very useful, because everybody was timing them on different machines. It was just impossible to compare. So I think this is great, and this is a good first step in just whenever you're trying to answer a question, do a systematic comparison first, do a systematic measurement. I mean, that's how you start. Without that, you're just talking. You know, this is what lets you answer questions.
But it's more than that. Sort of the wonderful thing that he was trying to ask correct questions. Sort of, what if I go from trees to hash tables? What if I do this or that? Trying to extending this. So that is very, very good. And in some sense, that's what we would like you to start doing when you're programming. Try different things, measure them. There are different alternatives. See what they cost. By the way, it doesn't take that long. You say, no, but in practical code. No, in practical code, it also doesn't take that long. You know, trying different data structures and see what kind of time you get is a very solid thing to do. It's easy, it's simple, you get some idea, and I learned enormous amount of stuff by doing simple experiments. And people always say, well, but this is not well thought through. No experiment is well thought through. I mean, you have to learn, bravely measure. You should be humble enough and know that somebody else could go and do some other measurement which will show something else. But that should not prevent you from measuring.
Some measurement is better than a perfect measurement. You have to start somewhere.
Oh, it's infinitely better than no measurements.
Yes.
Yes? And people do not, again, sort of people talk, at least talk about unit tests. We don't write them, but at least we talk about them. But we should not just have unit tests, we have to have micro benchmarks by comparing different solutions. That should become, in some sense, a habit of a programmer, of saying, look, I will try this, I'll try that, I'll measure. And I'll write down a little sort of note so that people could, this. So this is why I think, just doing such small table is very, very good. Is it better than extensive report on, benchmarking of all possible data structures? No, but, this is a very good start. And for most of us, this is actually sufficient. It gives us an idea of how different data structures will affect that.
And if you have a 10% difference, you say, okay, maybe further study is needed. If you have a 10x difference, like, well,
Well, actually, if you have 10% difference, no further study is needed. Who cares?
Right.
Right? And if there's 10 times difference, also no further study is needed. I mean, you have to do the fast one. Yes, there are complicated cases, but usually life is simple, actually.
So actually, let's first talk about the question that Chetan was trying to answer, which is that, this algorithm, for all its inefficiencies, is ultimately an n log k algorithm, where n is the number of words and k is the number of unique bigrams, because these structures are log k in their asymptotic complexity, right? Whereas sorting this thing is going to be n log n, and so like, okay, at some point, if n is large enough, this should start winning, right? That was the conjecture, and so he was trying larger and larger data sets to see when will we get there, right? But so the key thing here is, why did he not get there, right? How large is log n? I mean, log n for real computers is what? I don't know, 35?
32.
For any real data set, this is a very small number. And so if your extra memory cost is 200x or whatever, this is not going to matter. Right? Log n is a very small number. 2 digits, less than 40 most probably, less than 30 in most cases. Right? So yeah, so that's one thing. Another interesting thing was the initial implementation that Nick sent out was this Python implementation that beats the C++ Smalltalk.cpp implementation by a huge margin, like, well, 50%, right? And that's a very interesting implementation to look at for multiple reasons. Well, one, it dramatically shows you the fact that it's not the language, it's your data structures, right? So that was using a hash table instead of a map. It was a little faster. It was faster, right? So if it doesn't matter it doesn't really matter if your interpreter loop is slow. If you're spending all your time in your data structure implementation, which is written in C, it's going to be fast. Whether Another thing it demonstrates is that you really need to know the language you're using, right? So I remember the way Nick described it was, I wasn't trying to make it fast, I just wrote an initial version just to see, right? But if you carefully look at what he wrote, it's very interesting, right? What does it do? Reads the entire file into memory and splits it, so you get just a list of words. Then there is this wonderful Python set of tools called, there's a library called iter tools, right, which has a whole bunch of very interesting things in it. And so, okay, let's take an iterator over this entire thing, shift it by 1, and zip it up. That gives you the bigrams. So you get bigrams from this, and then you just count them, right? And then how do you find the largest ones? You use a heap queue, a priority queue, right? So this is actually, I tried to make it faster, and I maybe single-digit %, but really this is very fast. And this illustrates that you really need to know your language well in order to use it effectively. You need to know that there are tools like iSlice and iZip and heapqueue in your standard library. If you don't, and if you write this using a naked for loop, it's going to be much slower. Right? So it's very important to know. The language doesn't matter, but it is very important to know what you are using. What is the language? What are the costs of doing various operations on in that language? What is provided by the standard library? Right? Do you know that there's a heapqueue module in the standard library? It's been around since the pre-1.6 days, I believe. Right? So it's not. So for instance, there's in the newer versions of Python, you can simplify this further because they added a class that does some of this automatically. There's a class called counter in the collections library. But you need to know about iterators. You need to know that itertools gives you much better performance than writing your for loop by hand.
This is true. I programmed in MATLAB and R, and in those languages, like if you're running a for loop, you're doing it wrong, basically, because you're in this interpreter, and in those languages, MATLAB it's arrays, right? It's like Fortran. Just anything you can do, if you can turn it into a matrix operation, you'll be fast. If it's a for loop, it's going to be slow. And then it's true for Python. I was just surprised. I guess I didn't realize that itertools was natively implemented. And in general, in the Python standard library, that's not generally true. And in some cases, you even have to know that there's a Python version and there's a C version as a weird name. You should just use the native version when it's there, because it'll be much faster.
There is another very important point. Observe that what we were saying, do not use advanced data structures when you program in C++. What Nick just said is the opposite, and he is right. When you are in Python, use advanced data structures. Right? So the strength of Python is that it has these pre-canned fast libraries. So if you use hash maps or whatever in Python, this is good. If you use the same stuff in C++ versus arrays, it would be bad. So again, you have to realize sort of relative cost of different things. Yes?
I think the nice thing about this implementation is that what it tries to do is not to move data around. You read it once because you have to read it into memory, and then all these beautiful ETL tools is just pointers over the data which you already have. If you try to modify this with list comprehension or other Pythonian things, it becomes 10 times slower because you start moving things around and mallocing. So
absolutely.
My take when I saw this code is never move things in memory unless you really have to create a new one. Always use I stuff.
Absolutely. Absolutely.
But again, you have to know, don't create, chains of A refers to B refers to C refers to D to avoid copying, because that might be more cool.
Basically, the bottom line is know exactly what happens on the machine when you write your code.
Know what's going on, right?
So I had another life, I was a JavaScript programmer, and we were trying to build up HTML structures using JavaScript versus just concatenating strings and just parsing them with the HTML parser. And one of my coworkers said, parsing HTML in JavaScript is free, because you basically, if you built up a big string and told it, hey, parse this, the browser was really good at parsing HTML. But if you create all these little objects and the JavaScript interpreter was doing it, it was much, much slower. So some of these things that you think, in this particular language, this operation's free. Parsing HTML in JavaScript is free. In this case, some of these other things they're free in the sense relative to implementing it yourself in the interpreted layer.
Food.